Petr Vozka is assistant professor of analytical chemistry at California State, LA, California State University, LA. He did his PhD at Purdue University, and he's the director of the Complex Chemical Composition Analysis Laboratory. His research focuses on the characterization of complex mixtures via state-of-the-art techniques, some of which we all know and love, and is the reason why he's here to speak to us today about his research. So the title of the presentation is Quantitative Analysis of Aliphatic Olefins in Fuels Made from Plastic Waste by Comprehensive Two-Dimensional Gas Chromatography.
Hello, everyone. Can you hear me? Good morning. Good morning. It's amazing to be here after 2 years of these events being online. It's really a pleasure. I'm really looking forward to talking to most of you in the next 2 or 3 days, and I hope you have the same spirit. It will be amazing. What I'll talk about today is a method we developed or we're trying to develop, but first, maybe here. So first, it's like a tradition to talk about the GC by GC. So is there anyone new in the MDC group? Like anyone? I hope there is someone new that is interested in multidimensional separations. So I'll give a little overview of the GC by GC technique. Then I'll talk about the quantitative analysis of aliphatic olefins in fuels made from plastic waste by GCGC, and then I'll talk a little bit about the academic or the way we're trying to implement the GCGC in our like teaching world as a professors. So let me start with this figure. This was a cool meme in 2020. It is not cool anymore, but you may remember this, how it started, how it's going, meme. So what you can see here on these two figures on the left, both of these figures are actually jet fuel. So on the left one, this is the one-dimensional chromatogram that you are probably used to. So if you count very well, you can probably count 200, 250 peaks. If you have additional like tools like mass spectrometry, you can deconvolute some of these peaks, so you can find more than 250 compounds. But the problem here is that there is a peak capacity limitation. So the figure on the right is a beautiful 3D figure from a Chromato software, which looks pretty cool on the picture for the presentation. But we never use this. We never use this 3D figure. So what we use instead is we look at this figure from the bird perspective. So okay. So we would look from the top, and you can see like these blobs. And then if you count the peaks here, there is over 1,500 peaks. So meaning there's over 1,500 compounds. If you have mass spectrometry, you can probably figure it out what these compounds are. Probably not all of them, but most of them. If you have some quantitative detector like FID, you can figure it out what is the quantity of these peaks, what is the quantity of these compounds. And so it's very powerful from where we started to where we get. To explain how the GCGC works, if you forget about this part, then you have your regular gas chromatography, right? So you have your carrier gas flow. It's usually helium, not anymore these times because of the prices. So we're switching to different inerts. You inject your sample. It's first separated on the first dimension column, which you are all used to, classical diameters, classical lengths. Then the primary column is connected to the secondary column. The connection doesn't have to be before the modulator, it could be after. It's really up to you how you decide to do that. And then you have your second modulator, your secondary oven, and your secondary column. So whatever is not separated on the primary column, you hope is going to get separated on the secondary column, then it goes to the detector. Now, the next slide I have here, this is from Christina Kelly from LICO. Christina is not, she couldn't come today, but at least her slide arrived. So she allowed me to use it. So one more time. So what's happening? So the sample is injected on the set of two columns. So the primary column separates the analyte the typical GC way. So that's how these are separated. Then there is a modulator. I'll talk about it a little bit. And so then these analytes are modulated and then released onto the secondary column. And once they are released to the secondary column, they are separated based on a different mechanism, meaning these two columns should not be the same. And that's how the GCGC is made. Talking about the modulators, there is multiple modulators. We're using thermal modulator. Many of you using probably also the flow modulator. But anyway, there is always the competition, which one is better. It really depends on your applications, but we can discuss it later. And then I showed you this figure, but if you don't have a mass spec, then you really don't know what these compounds are. And so what you need to do if you have, for instance, flame ionization detection, you need to do something painful, which is called classification. So you basically need to tell your instrument what these compounds are. So you need to develop this classification. Many of you are part of the new ASTM, the 8396, I believe. So is anyone participating in 8396? Okay, few. So just briefly, there will be a guided discussion tomorrow, I believe. So please come. This is the first time the GCGC was implemented in ASTM for the field purposes. Right now, we are in the process, or everyone is in the process of getting some reproducibility data. So we need to develop this classification. Very briefly, this is a reverse phase. So you have your N-alkanes right here, all your isoalkenes above, cycloalkenes in the middle, and then the aromatics on the bottom. You can do this detailed classification. You can distinguish these compounds based on the carbon number. You don't have to do it that detailed, but we like to do it, which is good because then you can get results looking like this. Let me zoom something. So for basically every hydrocarbon class and for each carbon number, you can get the weight percent in that region. Now, GCGC is most of the time used for analysis of complex chemical mixtures. For some examples that we are actually GCGC for is the petroleum products, beach oil spills, and microplastics analysis. Many of you using it for different ways: food mix, petroleum mix, and many others. So this is the example that we're using the GCGC for. Now, let me move to the real project, to something that we are using the GCGC for. So many of you have seen these pictures of the polluted ocean. You can tell that I love turtles. These are nice pictures, but you can see a little bit like worse pictures looking like this. I usually ask people how much of the plastic waste they think is ending up in the ocean. So think of a number. How many percent do you think is ending up in the ocean out of the plastic waste every year? Now, if your number was more than 3%, then you are wrong. So only 3% of plastic waste is actually ending up in the ocean. So the expert says that by 2050, there will be more plastic than the fish in the ocean. So where is the rest of the plastic? It's actually landfill. So more than 76% of the plastic waste is landfilled. And here are some predictions. So right now we're here, 2020. And you can see that the prediction doesn't look very good. The majority of the plastic waste, over 76%, is the polyolefinic plastic waste, meaning polyethylene and polypropylene. The problem with the plastic waste is it doesn't go anywhere. It just degrades to microplastics, which we all breathe and inhale, and what else? So approximately 5 grams of the microplastics every week we get in our body. And so we were thinking, or people, smart people, were thinking what we can do about this. And so we start collaborating with 2 universities. One is the University of Chemistry and Technology in Prague. I think someone, Miloš from the university, is here, right there. So they work on pyrolysis. They pyrolyze, or let me skip this. And with Purdue University, I don't think anyone from Purdue is here. No. So both of these universities, they have a technology, they convert plastic waste to fuels, one using pyrolysis, other one using hydrothermal processing, using different feedstock like plastic falls, waste tires, and the polyolefinic plastic waste. With Purdue, we already published 2 papers. You can read them if you're interested. With Miloš and with the UCT Prague, we have a paper under review, so hoping it will be published soon. Here are some chromatograms of how these fuel look like. So this is regular diesel fuel. Forget about the colors now. This is the hydrothermal processing diesel fuel. So I'm not trying. I'm not hoping that you will gain some information from this. I'm just trying to show you how complex the mixture is. It's not only a few compounds, really like thousands or hundreds of compounds. This is a fuel from the UCT Prague. Again, a lot of compounds. So you really need a powerful technique to separate these and to quantify these. And so once we did that, we got all these numbers. What's the reason we're doing this? Well, one of the things is that we were able to develop the reaction pathways. So here you can see reaction pathways for the polyethylene and polypropylene depolymerization. Again, it's not very important. What is important here is that no matter if it's polyethylene or polypropylene, all of these at one point became olefins. If you think about the chains, if you break it, you will get double bond on one side, you will get radical on the other. So it makes sense. The thing is that if you don't go all the way to here, in your fuel, in your product, I shouldn't say fuel, it's a fuel-like product, you will end up having a lot of olefins, or alkenes, if you will. And olefins, we don't have a methods to quantify olefins. There are some methods I'll talk about at the end, like bromine number, iodine value, if you're familiar with those. But these doesn't tell you much. These, for example, bromine number is number of how many grams of bromine is necessary for 100 grams of fuel. Doesn't tell you much about what these olefins are. So what we were thinking is let's develop a method when we can really quantify and get like detailed quantification of these alkenes. And so when I showed you this classification, that was not 100% true because as we discovered, or as the world knows already, between the isoalkanes, we also have a lot of isoalkenes. Between the monocycle alkanes, we have a lot of linear and cycle alkenes with one double bond, and so on. Cycle alkenes, tricycle alkenes, we have a lot of tricycle alkanes. And with aromatics, we have a lot of aromatic olefins. So at the end, it's a mess. And we were thinking, is there a way to develop a method so we don't have to go compound by compound and trying to figure out what is each compound and just do it like quickly, fast, and yeah, in a nice time manner. So we came up with, we didn't came up, but we tried this derivatization method when we're using the methyl disulfide and iodine solution. So we basically take the sample, we run it as this, and then we take the sample, we derivatize it, we run it for the second time, and then whatever is the theory is that if you derivatize your sample, you will get rid of the double bond and you will get these two methyl sulfide groups at the end, which means this compound will become heavier. So it will move to the right if you're using normal phase, reverse phase, normal phase as well. And then it will become more polar, so it will move to the bottom. So basically these peaks ideally should shift from the original region somewhere else. Now the goal was, if we run it before and after, if we find what the difference is, we know the difference should be the olefins and we should be able to quantify this. So very briefly, thanks to this, we should be able to quantify the isoalkenes, olefins with one double bond plus linear together, two double bonds and three double bonds. Now, if you think about, the way we do that is for whatever olefin, for whatever carbon number, whatever hydrocarbon group, we take the peak area pre-derivatization from the same area, and we take the peak area post-derivatization and normalization. So for instance, if you would like to quantify the isoalkene C11, you take the peak area pre-derivatization C11, you subtract the post-derivatization normalization in the same area. Now, if these are your N-alkanes, these are actually your isoalkanes, linear alkenes. So if you would like to quantify those as well, the same way you classify the N-alkanes, you can classify the linear alkanes, and you can actually from these, you would be able to also quantify the isoalkanes separately. So you don't have to group them. So here are some preliminary data. This is a sample from UCT Prague. So in this case, let's for instance focus on the monocycle alkene C11. So these monocycle alkene C11, in the original region, there was 1.59 weight% of these hydrocarbons. And then after the derivatization and calculation, we were able to figure it out that actually only 0.91 was the real cycle alkane, the rest was the olefins. And so we can really do that very detailed for basically each carbon number, each hydrocarbon class. If I zoom out a little, if you would like to get the totals, so for all of these groups, we can always separate and quantify for non-olefins and olefins. So we can do it this way. Now, we were looking for methods how to validate this method. And it's really not easy whenever you came up with something new with GCxGC. The only way you can validate this by some standards, you really have to use all of the standards available. So that's what we did. So these were 9 gasoline-like samples. So we measured for all of these samples. We measured, as I already mentioned, the iodine volume, which is ASTM 4607, bromine number, and then the FIA. FIA is the standard method for the hydrocarbon types in liquid petroleum products by fluorescent indicator absorption. And so we got the numbers for all of these 3 methods. However, as I mentioned, these numbers are not very detailed. So basically the iodine value is giving you the grams of iodine per 100 grams of your sample. Bromine number, very similar. The only something that very similar to what we're getting is the FIA method, which is giving you the volumetric percent. So basically what we try to do, we compare the trends. So you can see the first one, there's the iodine volume. So that's, we actually selected these 9 samples. So we would cover the amount of the olefins between 0 and 50 weight%. Okay, so you can, if you compare the trends, these trends fit. And then if you actually compare the FIA, which is volumetric percent versus the GCxGC, which is weight%, so these are also very close. We don't have, for some samples, we don't have these results, but you can see that these are also very close. So that's the only way we could so far validate the results. Usually people talk about the good ways or the good things about their method. There are, of course, some disadvantages in this method. One of them is the iodine, which is hard to buy in some places. It took us 8 months to get it in California. So another thing is the DMDS. DMDS is kind of smelly. So if you do it in the fume hoods, you're good. Sometimes the whole floor smells like DMDS, which is not good, but it just happens. But the main, all of these you can overcome, but the main problem is that if you think about what's happening there, the heavier isoalkanes actually not shifting all the way to aromatics. So for example, here you can see, so the results I showed you were for the gasoline-like sample. This is a diesel-like sample. So if you look here, this is a diesel sample. To zoom in, this is the region where you have a heavier 3-cycle alkenes. So this is a region when you don't expect anything to see if everything is shifting in the aromatics. This is the border between the aromatics and non-aromatic. And then this is after the derivatization. So you can see that a lot of these compounds, because they are heavy, they don't reach all the way to the aromatics. So they actually move into this region. And now we get into the same problem. We would have to go compound by compound to figure it out. What are these, which is annoying. That was the original goal to not do so. So this method is very nice and working for basically the fuels. They don't have anything in this region. Okay, so that's all the gasoline fuels and some like lighter diesel fuels. Moving towards something heavier, that's the problem. So we know about this. So what's the next step we want to do? We want to validate the results using GCGC ToughMS, which we are getting soon. So we're getting the Pegasus BT4D, and will be for the first time able. If I didn't mention this, so all of this was developed using the GCGC FID. So we never had an option to look what these compounds are. So now for the first time, we'll be able to figure out what these compounds are and validate, hopefully, using the GCGC ToughMS. Another thing is to attempt to use the chromatography or to beg Dr. Sinova group for their help with the chromatography, because that might be like a beautiful example how the chromatography should figure it out, because it's pre and post, so that hopefully we can gain some knowledge there as well. And then one more thing is that we might try to use different derivatization methods. We were thinking of some like oxidative derivatizations where you don't have any byproducts, anything, any toxic byproducts. You just bubble ozone through your sample or something like that. So that's another potential ways we'll be looking into. What I also didn't mention is that we don't have PhD students, so all of this was developed by my undergraduate and master students. So one of the students is Genesis. Genesis is here. She'll be present in poster as well. So go and talk to her. Then it was Estella and Hung. And so, yeah, I'm very excited to working with my students on this. Now I'll be moving towards the teaching and what we're trying to do in the academia with the GCGC. So it's not official yet, but you might notice that I have a lot of LICO instruments. So we start collaborating with LICO. Our university is a little bit like a specific in terms of the students we have. So California State University is proud being #1 in upward mobility. If you don't know what it means, I don't blame you, I didn't either. So basically we take the poorest students from the bottom 20% and we turn them into the most rich people, upper 20%. And it's not very uncommon that you have in the class homeless students. So that's what we deal with. And so we were thinking, what can we do for our students to improve their lives, to, just put them on a good track. And so LICO was on board with this idea. So we already working on a GCGC training / research facility, which is the collaboration between LICO and our lab. We already have these two instruments there. So we have a Pegasus BT, GC ToughMS. We have a QuadJet, which is the GCGC FID. We also have Agilent's GC-MS FID. So that's basically the road students learning. They will start working with simple GC-MS, GC-FID. Then they move to Pegasus GC, learning with new software. Then they move into GCGC, and then finally they will be now, working and learning with the GCGC ToughMS. We also have both of these softwares. We're still working to learn the chromatography, but hopefully we'll get some help. So the goal is that the students, it doesn't have to be just students, it could be faculty members, it could be students from different universities coming and learning basically in this facility. What I'm trying to do is my students or whoever is coming, they not only running the samples and learning these things by not touching and playing with the instruments. So we have one class on campus which is called Advanced Separation Techniques, Analytical Separation, and Mass Spectrometry. And whenever I heard the term Advanced Separation Techniques, I believe it should be advanced course. So what I did, and you guys can do that as well, I asked for free stuff from the vendors. So is there anyone from Agilent? No, so Agilent sent us a lot of stuff. LICO sent us a lot of stuff. It's not probably very nicely seen here, but here you can even see the EI source. So they send us free EI source, probably broken, I don't know. But the good thing is that if you have these free stuff, because whenever you want to show your students or whoever how to take apart or put together the EI source, you don't want to shut down your instruments. You don't want to remove it all the time, right? I mean, come on. So with this, you can do that actually. So I also redesigned a curriculum where we put the GCGC instruments and other instruments in the students do experiments with these instruments. And I also let students practice on the real instruments, but again, I wouldn't shut down, the GC MS just so they can play with the EI source. But whenever we can take apart the FID or like smaller things like this. I have here a short video. So what we do in the course, we usually set up like 3 stations. One is where the students learn how to cut the columns, which earlier can do. This is the EI when they can take it apart, put it back together in groups. And then we also get a lot of inlet stuff. So basically in this station, they can, put all the inlet parts together to figure out how it really works. So that's what we try to do. That's probably it from me. This is my information. If you would like to reach out, please feel free. So this is the most important part for my students. So we started Instagram page. So if you can take out your phones right now and start following us, that would be